In this video, we're going to discuss something called the limit comparison test. So limit comparison test. So the limit comparison test is a really powerful test that works whenever the direct comparison test works, and it basically allows you to bypass all of the inequalities that you have to create when you're using direct comparison. Let's abbreviate it with LCT. So it's a really useful test. So if you don't like the direct comparison test, limit comparison is much easier to use. The downside is it requires more writing. So the hypothesis is that you have A sub n positive and B sub n positive for all n, so they're always positive. And we're going to let the limit as n goes to infinity of A sub n over B sub n, we're going to set that equal to L, where L is a positive number. But textbooks never say it that way. They always say where L is finite and positive. I guess they want to emphasize that it can't be infinity. But you could just say positive number, and that's the same thing as finite and positive. So finite and positive. So what does this mean intuitively? If you think about it, this basically means that A sub n and B sub n, they have the same growth rate, right? The only way you're going to get a limit that's equal to a number is if you have maybe something like this. Say you have limit n goes to infinity, n squared plus 1 over 3n squared plus 2. In this case, they're both quadratic, and the limit is simply the ratio of the coefficients. So you see the growth rates are the same. So basically this is saying if you have A sub n and B sub n both positive, and they have the same growth rate, then the series should both behave the same. So the result of limit comparison is the following. Then the series, again, I'll omit the infinities like I usually do, or I sometimes do. These are infinite series. Then these series both converge or both diverge. So again, the intuition behind this is if this limit is equal to a positive number, then these both have the same growth rate. So in theory, these both should behave the same. They should either both converge or they should both diverge. Let's do one example of limit comparison so you see how to do it, how to show the work. So I'll just make one up. Here we go. Infinite sum, n runs from 1 to infinity. Let's do n plus 4. And on the bottom, we'll do 4n cubed plus 2n plus 7. So this is one where you wouldn't want to use direct comparison because you'd have to deal with the 4, and it just looks like it's a little bit more work. So to use limit comparison, what you do is you call this piece here A sub n, and then your B sub n, what you do is you just look at the leading terms. So in the numerator, that's n, and in the denominator, that's 4n cubed. So you just look at these leading terms here. So this will be 1 over 4n squared. That's the same thing as 1/4 times 1 over n squared. So that's going to be our B sub n. That always works. Almost all the time. There's a couple cases where it's a little bit different, but most of the time this will work. So you just take the leading terms here like this, and that's going to give you your B sub n. Okay, so now we just have to satisfy this definition, this test. So they're positive, so no worries there. We just have to take this limit. So let's take the limit as n approaches infinity of A sub n over B sub n. This is equal to the limit as n approaches infinity. So A sub n is this piece here. I'm just going to write it. N plus 4 over 4n cubed plus 2n plus 7. And then we're dividing by B sub n. You might say, oh, you didn't write it. You're right, I purposely didn't. So when we divide by b sub n, you really multiply by the reciprocal. So I'm just going to take this one and flip it. It's the same as this one. So 4n squared over 1. Right, because division is multiplication by the reciprocal. So typically you just write your a sub n, and then instead of dividing by b sub n, you just flip it and multiply. And if you look at this and you look at the leading terms, you're going to see that they're exactly the same. Look, 4n squared times n, that's going to be 4n cubed. And on the bottom we have a 4n cubed. So the answer is just 1. Okay, it's just 1. If you wanted to see an extra step, I can show it here. So you see it, it's really 4n cubed plus 16n squared over 4n cubed plus 2n plus 7. And then because the degrees match, it's the ratio of the coefficients, so it's 4 over 4, so it's 1. Yeah, worth showing that extra step just to make sure it's clear. So this is 1. So now you have to say which is finite and positive. Right, because this is the hypothesis of limit comparison. So what does this mean? This means we can use limit comparison. So LCT applies. So all we've done so far is establish that we can use the limit comparison test, right? We've taken the limit, we've said it's finite and positive, so we can use limit comparison. So what does limit comparison actually say? It says that they both converge or diverge. So now what we'll do is we'll explain why the sum of the b's diverges. So note, this infinite sum here, as n runs from 1 to infinity, of 1 over 4 times 1 over n squared, this converges by the p-test. Converges by the p-test, since p is equal to 2, which is bigger than 1. So what does that mean? That means that our original series also converges. So hence, our OG series, original, also converges by the LCT. And it's pretty much like a little proof. So I like to put a little box with an X. I mean, these problems, I mean, they're problems, but they're almost like little proofs. Everything is justified in a really elegant way. So you see the original problem. You identify your a sub n. Your b sub n, you always get it from these. You always just take this limit and just make sure to say it's finite and positive. So that means that you can use the limit comparison test. Limit comparison will say that the sum of the b's and the sum of the a's will either both converge or both diverge. So now here is where we explain that the sum of the b's converges by the p-test. Therefore, the sum of the a's must also converge, right? Because they both behave the same due to limit comparison. So it must also converge, but this time it's by the actual test, by the limit comparison test. It's really, really important that you understand the logic in these problems. And when you're doing these problems, whether it be for yourself, like you're just learning math for fun, or maybe you're taking a class, it's really important that everything is justified thoroughly. Higher level mathematics is often like this, except it's even more so like this. But this is kind of a glimpse into what you would do if you were taking like a class a math major would take. Everything is a careful argument. I hope this video has been helpful. Take care.